the University of Leeds, Great Britain. But he also has an adjunct
is built on
professorship
something called
from
gradients.
Mississippi State University.
A gradient is basically...
And he also has a Doctor of Science in Applied Mathematics from the University of Wales, and a PhD in combustion engineering from Cranfield University. And his scientific production includes more than 200 research articles, including combustion engineering and the relation between thermodynamics and information, which is the topic of the talk today, but also papers on biomimetics. And McIntosh, he's part of the United Kingdom branch of Answers in Genesis, and for many years he has been heavily involved in the creation design debate, and he travels all around the world and teaches about matters of origin, and you have also written several books, for instance, Genesis for Today and Wonders of Creation, Design in the Fallen World, together with Stuart Burgess. And you have also participated in a number of debates with atheists and evolutionary biologists. So, welcome, Andy. We are looking forward to your talk, and it's titled Some Observations Concerning the Thermodynamic Implications of the Endergonic Bonds in Living Systems. So, welcome.
Thank you very much. Could I just ask what time are we meant to be finishing my talk?
You have an hour.
An hour from 1:45, yeah. Okay, so in for 1:45. Okay, thanks ever so much, Ola. Okay, well, thank you ever so much, Ola, for your kind welcome. And I really appreciate being here. And also, it's thank you to Samuel, thank you to Horan, and it's been good to see Jorge from Norway, where I believe the conference is going to be in 2 years' time. And I just feel so much out of place, really, because what we've just heard about epigenetics, not only from the previous speaker just now, but also yesterday from Peter Borger and others, has really made me realize that there is so much to be done in the biological area. I've just begun to look at these things from an engineering point of view and thermodynamics. By the way, some of you, I know Yoga is coming to this, there's the mega conference coming up in England, so if you want to fly over to that, you'd be welcome, but you've got to book by October the 27th. If you don't do it by then, you won't get in. They put a deadline on when you can book by. Even though the conference is a week later, you've got to book by October the 27th. The books have been mentioned, they're there if you want to have a look at them, and there's quite a few pages there which you might just like to flick through if you're not sure. I've opened one of them so you can look at it. There's a booklet called Are You Really an Atheist? And there's also a booklet which is a summary of the big book as well. There's also another booklet I've produced on the aerodynamics of the Kingfisher. The photography is by a good friend of mine who's a brilliant photographer. Anyway, I want to talk to you about the language side. I want to talk to you about some observations on the thermodynamics of the DNA. So I want to talk a little bit about entropy and closed and open systems, and then the important section, and I'm going to move fairly quickly through the first three because you've probably heard, some of you have heard me talk about that before. But I want to get to this Landau principle, which is something which I've only recently written about, and I've begun to realize it's hugely relevant to the issue of the DNA. So as I say, I feel very much as an observer coming from a different discipline, looking at the enormity of what you are doing, and I feel that I'm just dabbling, putting my feet in the water of a massive ocean of problems and issues. But I hope you'll forgive me if I make mistakes in the way I label things, then do tell me. But I'm not so familiar with the biology language. I'm much more familiar with the engineering and mathematical language, which of course is what I'm trained in. Now, for many years, it was many years ago that I wrote a paper on information and the information in living systems. Did it come from a bottom-up approach or a top-down approach? And obviously, I was proposing a top-down approach. And this is ground which has already been covered, but I need to just bring some of you up to speed as to how I'm approaching things. There are two main laws. There's a third law of thermodynamics, and I'm going to refer to yet another one, which is a possible fourth law in a moment. But there are two main laws of thermodynamics, and that is that energy is neither created nor destroyed. The second law of thermodynamics is that in an isolated system, the amount of energy that cannot be used to do work is always increasing, and the energy loss per degree is called the entropy. So this presents a problem because it's an arrow of time problem, and as Danny Faulkner has pointed out, there is an inherent contradiction even in those first two laws, because the first one is saying that everything's been there from time immemorial, there's never been a beginning, and yet the second law is implying that there is a beginning. So you've got an inherent issue there, which of course is only resolved in the creation model, which clearly says that God is the infinity in the problem. He is the great God who has made everything, and yes, there is a beginning. But in a famous conversation with Professor Dawkins at one point on the radio, I never really had a formal interview with him, but there was a discussion. You can look it up if you wish. But he proposed that there's loads of energy out there which can actually make systems. But by doing that, he was trying to say that you don't need really any machinery to receive that energy, and the idea of ordered energy, that is energy which is specifically there dealing with machines, could just somehow arise out of nowhere. And that's what is being proposed by all evolutionists. When they are presented with the issue of thermodynamics, they say, well, it's an open system. Open systems have got energy flowing in from the sun or from other stars. It's not a problem. You can easily set up some sort of ordered energy system locally. But I'm going to ask the question, is that really true scientifically? Because although the second law, it's true, is to do with an isolated system, the principle underlying it is actually a very important one which we need to address. Photosynthesis, which was brilliantly talked about by Boris Schmidtgall yesterday, and I can't do justice to what he showed very clearly is an incredibly complicated system, but just in summary, what is happening thermodynamically is frankly astounding, because all the trillions of leaves which are out there at the moment in this beautiful autumn weather, we don't have it quite so beautiful in England, it's usually raining half the time, but here you've got beautiful autumn weather. It may be cold, but you're seeing gradually those leaves, of course, are changing, but in the spring and the summer, what they're doing is they're actually absorbing energy in a very specific way, such that the dead leaves that we are now making just heat up if you have the same energy coming in, doesn't do anything to them. So what's going on? Well, this is a very simplified version of what Boris was talking about yesterday, but the chlorophyll is absolutely essential on the surface of the leaf. The carbon dioxide, the water, and the radiant energy of the sun is then catalyzed by the chlorophyll to produce, as he's clearly said, I'm just dealing with the oxygenated examples. I know he was dealing with non-oxygen light machines, if you could call them, but they don't all produce oxygen. That was a good point that he made in the harvesting of living systems, but I'm just dealing with that which produces oxygen. Carbon dioxide, water, and the radiant energy from the sun with the catalyst of chlorophyll produces sugar, oxygen, and water. And some of the water is used. So you actually have got an important catalytic machinery which effectively makes that reaction take place. And it is therefore absolutely vital to say that that surface chemistry is available, a bit like a solar cell on a human-made system. A solar cell is absolutely essential to change the radiant energy of the sun into electricity. Here, the radiant energy of the sun is being changed into sugars, which are useful to the plant and at the same time is producing oxygen. So in a non-isolated system, so this is not now an isolated system as with the second law, in a non-isolated system, the free energy potential will never be greater than the total of that which was already initially in the isolated system and that coming in through the boundary. I'm not going to say that this is a law, but it does seem to be a principle. And I've written on this 10, 15 years ago, and you can find the papers, which I'll refer to in a moment, on the web, which I've written and others have written. And the free energy is the specific definition of an energy which is available to do work. Boris actually mentioned that the free energy is actually changed by this system of photosynthesis, and it causes the random energy coming in from the sun to be converted to something which is specifically useful to make the plant grow and to make living systems able to use it. We call it the Gibbs free energy for chemical systems, and it's the overall enthalpy, that's the energy, overall energy available, minus that which is lost due to entropy. So it's, if you like, it is the ordered energy or the organized energy in a system. So that question, which about where does the energy come from, which is able to do work in living systems, and Richard Dawkins said, oh, there's loads of energy out there to do it. Is that answer actually valid? And the answer is no, it's not. Random energy does not build the machinery which is absolutely vital to make living systems work. This thermodynamic principle that the free energy potential is never greater than the total of that which was there already plus that coming in through the boundary seems to be a ubiquitous principle for open systems. So let me just do a little bit more thermodynamics. I don't want to make your head hurt, but let me use some illustrations. This is in the book which Ola and Samuel produced. You'll find that this illustration is used in my chapter, and some people have found it helpful because this idea of the definition of a machine makes most people think of nuts and bolts. I'm not talking about nuts and bolts. I'm talking about I can't think of a better word to use. It's a combination of maybe chemical systems. It often is chemical systems. When you're dealing with living systems, it's usually biochemical. And those systems are either harnessing the energy, making it ready to do work, or else they're using the energy and converting it immediately into something which does work. Here's the book, by the way, which I'll just put that up there. That's the book that I'm referring to, where there is a chapter there which deals with this issue. So think of a machine rather like a hydroelectric dam. The water flows downhill and just goes into a river and goes into the sea, and you think how beautiful, but it's good, isn't it, if you can actually, both in Norway and in Scotland and where you've got mountains, you can sometimes make dams across the river and you can then harness that raw energy such that it's able to do work. And in living systems, endergonic reactions, so that is systems where you need energy in order to make these work. So they use energy, they don't give out energy. Most living systems machinery is like that. They have endergonic reactions. And they are often enabled by other machines like ATP synthase, which raise the free energy for the polymerization of DNA. ATP synthase makes ATP, which itself is an unstable molecule in a raised free energy condition, and it's ready to give off its energy in very specific ways. So just so that you understand this, I'm going to play a video which is produced at the Discovery site by Robert Statler. And he had a lot of discussions with me about putting these illustrations in. He's got a whole series, or the Discovery Institute has a whole series of what's called long story shorts videos. They're well worth watching if you want to get some ideas as to how to put things over in a way that young people can understand today. Here's this part of this.
Because life is built around something called gradients. A gradient is basically more of something over here and less of it over there. The opposite of a gradient is equilibrium. Physics loves equilibriums, but not so much gradients. For instance, water likes to be in equilibrium, all spread out evenly. But if you build a dam, you can create a gradient, collecting a bunch of water on one side and not a lot of water on the other side. The water naturally wants to flow down from the high side to the low side, and this is where energy can be harnessed. Life does the same thing, except instead of water, cells use proton gradients to capture energy. It's super important. No gradients, no life. To advance further toward life, we would need a continuous supply of these energy gradients and a way to harness them. Some scientists claim that there were plenty of energy sources to support the first proto-life forms. Hydrothermal vents.
Yeah, well, I won't play it all, but you get the idea. That's the type of way that the whole film goes on. I'll play another bit in a moment. ATP synthase, I mentioned earlier, makes ATP, and the ATP synthase is a vital machine. If without that, you'll never get living systems to have energy going down specific pathways. So just to illustrate that point and the fact that you need a machine in order to take in the raw energy such that it will be useful, Statler goes on in this film, mainly geared for young people, but I think most of us appreciate it, in order to illustrate the point that even for things like our mobile phones, we need energy in a very specific pathway. Hear him again.
It needs very specific kinds of energy, and it needs to be fed it in a very particular kind of way. Otherwise, it's kind of like trying to charge your cell phone with a charcoal grill. There's lots of energy in the grill, but none of it is usable for your poor, dying phone. To harness the raw energy of the grill into something your phone can use, you would need a set of pretty complex machines. A boiler to heat water into steam, a turbine that the steam pressure can spin, an electric generator, then transformers, converters, regulators to get the energy in just the right form. And then you need the right kind of charger plug thing for your phone, and if you're lucky, the cable's long enough so you can lay in bed while it charges, and that's a weird angle. But, like life, your cell phone isn't just picky, it's also fragile. Not only will the grill not charge your cell phone, but it'll also destroy it. If the little circuits and bits in your cell phone get too much energy, or even a little bit of the wrong kind of energy, it's done for. Oh, battery's almost dead. Let's get you some energy. 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 Raw forms of energy can only be used for life if complex machines are available to harness them. And the wrong kind of energy will destroy life.
So that's really an illustration of the fact that we all need something like ATP synthase, making ATP, which is then farmed into all sorts of usages. One of them, of course, is kinesin, which is also absolutely essential for life. But as the two legs of kinesin walk along the microtubules, which, by the way, are made as it goes along, you'll know, those of you who know the biochemistry well, that those 2 feet flip over partly because one of them is fed ATP, and it's the injection of the ATP right at the right moment which causes that to work. So there are a whole host of other areas. There is the polymerizing of DNA, which which can only be done by, again, injecting ATP. So free energy is a big issue in living systems, and that's something I've been learning in the last few years. Free energy, as I remind you, has a specific definition. Gibbs free energy, which is mainly what we're referring to here, is the overall energy available minus that which is going into entropic routes, because there's always a little bit going down routes which are not useful. Spontaneous chemical reactions move towards equilibrium and lower the free energy. Those are called exergonic reactions or exothermic reactions. The opposite is true for endergonic reactions, which raise the free energy. These are not spontaneous. So it's the ones on the left which you've got loads of in living systems. There is a further complication, and that is that ATP synthase cannot work without ADP, which is adenosine diphosphate. But that adenosine diphosphate, amazingly, already needs existing adenosine triphosphate in order for it to work. Lets this film make the point much better than I can.
Here's the paradox. The cell needs to make ADP, the empty batteries of life, before they can be charged up to ATP and put to use. But producing one new empty battery requires at least 7 already charged batteries.
That's the point I was making.
So you can't make ADP until you already have ATP around in the cell. And ATP is required to build ATP synthase. But ATP synthase is required to charge ADP into ATP. So life's energy harnessing process is one big paradox. You need it before you can have it, and you can't make it until you've already made it.
So there is one big paradox, and it's not just one, there's many paradoxes, where you've got chicken and egg situations, where here, this time, you've got chicken and egg and sort of a baby chick as well. So you've got a whole system which needs to be there in order to get anywhere with living systems. And as I said, the ATP is essential for building, for polymerizing DNA. So there are big thermodynamic issues. You won't get any progress in polymerizing DNA unless you've got this little guy, ATP, in order to push you over the top to make the delivery of the polymerization possible. And we basically call these problems in combustion, which is the area that I'm from, but I'm applying this knowledge to living systems. We basically call this problem the problem of activation energy. You've actually got an activation issue in the polymerization of DNA, or it might be in the use of ATP in making kinesin walk along those microtubules. ATP is used in a whole host of applications in the cell. So you've got this issue of having an energized, activation energy-based intermediate. You've got raw building blocks, and you cannot make them. I'm just thinking of polymerizing DNA at the moment, but there's many other applications. You can't actually get there just by simply taking the raw building blocks and hoping that they will come together and work. No, they won't, because there is a free energy problem. There is an activation energy problem. You have the raw building blocks, and you need to have an energized intermediate. And of course, the intermediate that you're using is ATP. But ATP itself, actually, if you investigate it, is not a molecule which really likes to be left alone. It will actually deteriorate very quickly. So how do we make DNA? As I've said, you've got to have an energized intermediate such that then the free energy change is negative, that is, it's a spontaneous reaction, and it then polymerizes. So there is a whole host of uphill thermodynamic problems, and this is connected now with information. I know it's making my head hurt, and I'm sure it's making your head hurt to think about these things in terms of thermodynamics, but that's my training. So when I see these digital information systems, I'm not only thinking about the incredible information base, and it's now become much worse as we think of epigenetics, which I'm not touching in this particular talk, and I feel that I've got an awful lot yet to learn. I'm mainly thinking about what are the energy pathways going on in this system. So let me now bring this let me just mention what I said at the beginning and the two papers that I am actually summarizing with what I've just been talking about in the last 20 minutes. So that's the basic issue that I've been addressing up to about a year ago. And the two papers that you can refer to are this one, Information and Entropy, Top-Down or Bottom-Up Developments in Living Systems. That was way back in 2009. And then there was another paper that I produced at an information conference way back in 2013, which John Sanford organized, and he produced a volume, eventually got it published, and it's the paper I've got in there is Information and Thermodynamics in Living Systems. But then I began to talk with this gentleman, Salvador Cordova, and I recommend him to you. He is an absolute brilliant guy. He's really a polymath. He won't like me saying it, but he is. Everything he writes about, he learns, he understands, and then he starts talking about it. And he's very good in the engineering. He's very good in the biology. He's worked a lot with John Sanford, who wrote the book Genetic Entropy and the Mystery of the Genome. Now he said, what about Landau? And I learned from him, and I went away and I read the papers, and I owe an awful lot to Salvador for this next point. You see, I've been searching for a long while for the connection between information and energy, and computer scientists know about Landau, and they know about all the work that he did in actually saying that there is a cost to producing information. In fact, he postulated that there is a minimum amount of energy, kT log 2 joules, associated with the erasure of a bit of information on a computer. This is approximately 3 × 10⁻21 joules at room temperature. K, of course, is Boltzmann's constant. So information has an energy cost. Any logically irreversible transformation of information, that is, where there is an output such that the input cannot be uniquely determined from that output, is necessarily accompanied by a kT log 2 joules of heat lost per bit of energy. Now that means that if you think that through, that the opposite situation of the storage of information then leads to the assertion that at least a free energy requirement of kT log 2 joules is needed to locally establish one bit of information on a substrate. Now let me repeat that point, because this is a crucial point. I had never realized this. But when I began to dig into the literature, I realized that Landau's principle has in fact been verified. Many people were skeptical at the beginning. They said, well, it sounds like this guy really, has put a lot of thought into it, but how can you prove it? Well, I'll come to that in a moment. But if he's right, then it means that whenever you store a bit of information, you've got a necessary energy penalty in order to store that information. So there is a direct connection, Landau is proposing, between storage of information, which we know from a creation perspective is immaterial. Of course, the evolutionists won't accept that, but that is the position that I have. Information is actually controlling, as we just heard brilliantly put by Tommy Alto in epigenetics. We thought earlier it was a DNA-controlled system. No, it's an epigenetic-controlled system. And I said to her, well, do we know what the epigenetic code is? And we don't yet. But eventually, I guess, way down the line after I've gone, probably 20, 30 years' time, somebody will eventually crack how to express the epigenetic code. But the principle still applies that the epigenetic code is controlling the substrate, which is all the biochemistry, right? All the energy pathways. So the energy pathway connected with the storage of one bit of information is a definite value. That's what Landau was saying. Now, that's a very important point. Now, this was eventually proved. It was a very complicated laser experiment, and it was actually had a potential well and the moving of one bit of information to another potential well, and they measured the energy transfer, and indeed it was Landau's limit. Other people have done this, and they've basically come to the conclusion that Landau, after a long back and forth in the literature where he was disbelieved, but most people now accept that what he said was correct. Now, this has implications. I'll just mention this. I won't be able to develop this line of thought. But there is implications here about cognition, which is knowing something in your mind, okay? There is a whole lot of philosophical implications as well. Just let me read to you from this paper in 2021, where Hemo and Schenker we're talking about the second law of thermodynamics in the context of cognitive science. And this is what they wrote. For those that think that the second law is universally true and that physics is causally closed, and want at the same time to endorse the computational theory of mind, okay, and that's because they're evolutionists, this is bad news. It seems to us that the dilemma we have put forward for the computational theory of the mind shows that the view that the mind is essentially computational has no place in a physical world. In other words, computational neuroscience turns out to be a non-physicalist view of the mind. And then he says he's got a get-out clause. Fortunately, there is a good alternative by endorsing a full-blown type identity theory of the mind, such as flat physicalism, in which the psychological states and processes and properties are reduced with no remainder to physical ones. This is the only way in which a theory of mind can be compatible with physicalism. Non-reductive views in cognition and brain science are not an option. So basically, he's saying that I'm forced to say that we're just sort of programmed machines on legs. That's really where he ends up. And he basically is shooting any idea of original thought. He's basically shooting himself in the foot. But I could go on to that, but I've put it here. Put another way, they are effectively saying that the independence of rationality in individual minds is not consistent with materialism, where the whole of physics is causally closed. So in other words, as Dawkins said on one occasion when he was interviewed by one of my colleagues in open air work, he happened to be walking through Oxford, and this gentleman, whom I know well, does open air work, said to Richard Dawkins, because he just happened to meet him, started talking to him about gospel matters. And he said to him in a very courteous way, Professor Dawkins, where does your mind come from? Because he was trying to get him to realize that he'd got a brilliant mind and it was created by God. And he got so frustrated with my friend, who was being very courteous, he said, my brain is just a lump of meat. The answer to which, of course, is, if his brain is just a lump of meat, why should we believe anything that he says? Do you see the point? If you say that your rationality is just the product of a machine, then there is no reason for one to believe that you are correct in anything that you say. And that's the problem that these guys are facing. Because this has big implications on cognitive science. Because they're trying to say that we are just material beings, that the idea of a mind is a ghost in the machine, as one person has said. Anyway, there's far more that could be said on that. I want to move on, because now I want you to just see that I'm only dabbling right at the edge of something which is much bigger, right? And there is much more to be done. Really what I'm doing here is just reviewing, and that's what I've written a paper on this to go in the book of the proceedings of this, and I've called it a review. I'm not giving you anything new which hasn't not yet been written about. I'm not going further than what I've already written about, because in the International Conference on Creation 2023, I produced a paper on this matter, right? So I haven't gone beyond that. So I've carefully said in the article based on this this talk for this conference that it's only a review, because frankly you could go away and read what I've written and you can see that I'm just simply talking about what I've done thus far. But I am showing to you that there is a whole area here which needs exploring further, and I'm still working on it. Now, I'm very grateful to many guys, and this is one of the most important papers, who've actually mapped out the genetic code and the energy levels in the nucleotides. Now, it took me a long while to work through their charts of the energy levels in, it was looking at the, now I'm going to struggle with this. It's what's the female section of the code, which, mitochondrial DNA. They're looking at mitochondrial DNA, and they're looking at the free energy bonds, right, in that area. They had written it in calories, so I had to convert it to joules, and eventually I got it, I understood what they'd done in terms that I'm more familiar with. So this is probably the most important chart in the whole talk. I worked out the positive free energy bonds for the triplets of the DNA, triplets of the nucleotides in the DNA. And of course, they're all positive, but they've all got different values, and they code for particular amino acids, which are listed at the bottom here. So you got your first one, so you may have T, right? Then you would have the next one, which would be T, C, and then you would go along the chart to look for the third one, okay? So each time you've got, so if you've got G going with, so this is the coding side. Obviously, the G will go, as we were just told in the last talk, the G will go on the other side to C. But this is looking at the list of the codons, right, on the coding side. So it may be G, if you look at the bottom one, G, then T, right? So you've got 15.5 against T. So GTT would have 15.5 joules for that codon to be fitted together. So this is raised free energy. So you've got a whole list now of different energies. But now when you look at these very carefully, and I'm putting the chart's still there, but now I'm making comments about it. The lowest free energy of the table is that required to stabilize ATA and TAT, which is 11.7 kilojoules per mole per triplet, which translates approximately to 19.4 times 10 to the minus 21 joules per triplet, which is approximately 6.5 times the Landau limit for a bit of information. Now, there's more that could be said on that. I've had further discussions with Salvador and others. In fact, the reviewer for this conference made a very similar point to what others have made, which is that this is much closer to actually being the Landau limit. I won't go into that just at this moment because it depends on how you translate from the codon to a bit, but it's certainly looking extremely close. So it is a very, very amazingly efficient system, which is, of course, what you'd expect because the creator is brilliant. And he has made a system which is very, very close to being the most efficient system that you could possibly get for storing information. There is a significant amount of energy that must be injected into the system along a very precise pathway to cause each of these 64 DNA triplet codons to form and to be maintained in this non-equilibrium state. So the idea that loads of energy out there could build DNA is frankly, utterly thermodynamic nonsense. You could only do it if you've got very specific energy pathways, and of course the ATP is ATP synthase, and the ATP that comes out of it is very much involved in this polymerization process for the phosphates, but it's also involved in making sure that the nucleotide bonds, the rungs of the double helix of the DNA, that's what we're talking about, that those rungs actually are going to have the appropriate amount of energy put in to make them work. Now, this whole principle needs to be taken further. I haven't yet done it, but I'm being urged by others to do it, which is to go for the simplest possible amino acid and then the simplest possible protein, and to work out all the energy calculation for that, and to see how efficient that system is, and to see whether we're very close, again, to Landau limits in those energy bonds. I haven't yet done that, but it's asking for that to be done. So I would encourage you to realize that there is not just an information issue, there is an energy, there's an energy associated with information issue. We could actually look at some of the papers where a lot of work's already been done on DNA replication. Some people have already done calculations on the astonishing efficiency of replicating DNA. So this is another point which has already been done in the literature by those who are not friendly to our position. People called Kempes and others have computed the DNA replicating efficiency of bacteria to be 5.8 times 10 to the minus 20 joules per nucleotide, and roughly 10 times the estimated Landau value of what we've already calculated. This shows that in replication, there is astonishing efficiency going on. They go on to say that the best supercomputers perform a bit of operation at approximately 5.27 times 10 to the minus 13 joules per bit, which is 8 orders of magnitude worse than the Landau limit of 3 times 10 to the minus 21 per bit. So I would suggest to you that there is, carefully put, there is definitely an apologetic here for the amazing design of living systems. Whatever information is stored in biological system, it is using a raised free energy to connect it to the substrate, and that this energy can be measured and is close to, but still just above the Landau value. Secondly, such systems for locally raising the free energy on the DNA substrate nucleotide bonds require a mind to channel precisely the right amount of chemical energy down specific pathways to achieve this. More research is required to experimentally confirm the connection of non-material information with measurable raised free energies in many other genomic sequences, and to show how close these codon delta G values are to the Landau limit. It's hardly surprising that our main opponents, people like Bill Gates, Richard Dawkins, and others have said these things. Craig Venter, for instance, has said, life is a DNA software system containing digital information or digital code. Dawkins said, the machine code of the genes is uncannily computer-like, but he hasn't realized just to how close it is to the issues that I've been raising concerning the Landau limit. So let me just say some closing words about information. And I'm very much dependent on my good friend Werner Gitt for these next 2 points. He actually makes the point that information transmission has actually 5 levels. I'm only going to take 2 of them. He talks about 5 levels, and I'm not saying he's wrong. It's just that in order to get this across to people who haven't thought into this, it's probably better to think about these 2 stages first. Message transcends the language or the code used. So if I want to say to Mary that John loves Mary, it might be better if John did it, then, you know, he's going to use a language like English or Swedish or whatever Mary speaks. But the language isn't really the measure of the message, is it? The message transcends the language. This was beautifully understood, that this point about message transcending the language, when the Rosetta Stone was discovered by Pierre Bouchard in 1799, where the same message was written in Demotic and in Greek, if I remember rightly, and in, of course, Egyptian hieroglyphics. So the message was not defined by the code. So you could have used, of course, the bottom one, which is Morse code, which says John loves Mary. So you are not dependent on the language for the message. But there is another point, and as I say, Werner Gitt would put 5 levels here, and I don't deny the truth of what he says, but if I could just get over 2, that would be something. The language and the code transcends the material on which it's written. So the first point is that the message transcends the language or the code, but the language and the code transcends the substrate or the material. And of course that applies to the DNA that we were just considering, the DNA codons. The biochemistry is not what determines the code. The code is something independent to the material. The information is not the same as the material. And we've got a real winner on that point. There is no one who can really deny what we're saying, even though they tried to deny it in the evolutionary world. I was once at a conference which was discussing protein folding. And because I know a bit about thermodynamics, I was invited to go along. And it was in Illinois. I can't remember the name of the laboratories that we went to. But anyway, we were all sort of sat around the table. And they were trying to argue that the protein folding, of course, was something that was all material. I'm saying, could it be that there is a code outside which is governing the way the folds are taking place? Because there's massive thermodynamic issues, because there's a lot of humps, there's activation energies to go over, and the pathway is not obvious. Today, by doing lots and lots of experiments and doing artificial intelligence, they can run what would take a previous programmer years to do. They can do it in 5 minutes with AI, and they can eventually, using expert systems, work out what the folding should be. But even that's not foolproof. Basically, there is something governing the way the proteins fold, and that's not fully, even today, it's not fully understood. And when I said that it could be some sort of coding which is non-material, you could have heard a pin drop in the room. What? How dare you say that? Basically, was what I was being told or conveyed. So I don't think it went down very well. But let me just John Baumgartner spoke at a CRS conference in 2022, and he rightly said the following, and it's very incisive what he said. What is language? Language is simply encoded meaning. How is meaning encoded? First, small snippets of meaning are assigned to a set of tokens or symbols, which we usually refer to as words. The resulting set of words forms what is usually referred to as vocabulary. Second, a set of rules, usually referred to as grammar, is specified by which elements from the vocab may be joined together to create more complex meaning structures. The bit in red, language is a non-material reality. Because meaning is abstract and non-material, so is language. Language is merely encoded meaning. This is why the meaning of a linguistic message conveys, this is why the meaning a linguistic message conveys does not depend on its material carrier. A message, if reliably encoded and transmitted, is the same whether it is via paper, ink, magnetic disc, CD, chiseled on a rock, and so on. Meaning is independent of matter. A linguistic message, when reliably transmitted, is identical whether it is carried by acoustic waves through the air, like me now, relayed electronically, faxed, emailed, encrypted, sent through the mail on a DVD, or carried via smoke signals. The message has an identity and a reality independent of its material carrier. It's a brilliant quote. And when I heard him say that, I thought, wow, that's put very incisively. So, some of you will want to look at my papers to see this next point, and I'm not going to dwell on it, but John Sanford urged me to compare information with and the laws governing information with the laws governing thermodynamics. And there is a principle that information, that there is a first principle concerning information and language and communication, which is that apart from creative intelligence, information cannot be derived from nothing. And the second principle is that apart from a sustaining intelligence, all information degenerates. And you can see here a pattern which is very similar to the first and second laws of thermodynamics. I won't go into that further, but you can look up those papers if you want to see the parallel between information laws and thermodynamic laws. I need to draw it to a conclusion. My time's almost up. So my conclusions are this, that naturalistic origin, thank you for that, Samuel, that's very kind of you. I really do appreciate the way Samuel's been running the...
It's not Samuel.
Sorry, I beg your pardon, it's not Samuel's, it's somebody else, sorry. Beg your pardon, sorry. Philippe, sorry, I beg your pardon. Anyway, thank you, Philippe. Conclusions. Naturalistic origin of molecular machines is essentially against the thermodynamics of open systems. Thermodynamics drives everything to equilibrium. Open systems cannot of themselves build free energy. There is a tentative law or principle at the moment of thermodynamics for open systems. I don't feel I have the liberty to call it a law. If others agree with me, then it could become another law of thermodynamics. But I think we have to walk humbly in this area. And if others agree with me, then maybe it should then get written in stone that there is yet another law of thermodynamics for open systems. But it's not for me to do that. And this principle that I'm saying could become a law is that the free energy potential is never greater than the total of that which was there to begin with, and that coming in through the boundary. Okay? I suggest that could be a principle, maybe become a law. But others have to agree, because you can't go around, quote, making something a law and then somebody says, oh no, it's not a law. Let me just now bring it to a final conclusion. Information sits on matter and energy and uses it, but is not defined by it. It connects with matter and functions even at the molecular level. There are principles of information exchange which parallel, as I just showed you, the laws of thermodynamics. And the bit which is really only recent is this last bit. There is a minimum energy cost per bit of information stored in DNA, and it's jolly close to the Landau limit. Let me bring a spiritual dimension as I close. In Acts 17, verse 28, it says, "In him we live and move and have our being." I believe that's literal. I can only speak now because God allows it. I can only breathe now because God allows it. He could switch it off in a moment if he chose to do so. So it was that our Saviour stood apparently in the dock with Pilate in the seat of government or the seat of decision. Who was in control of who? If you read John 18, the Lord says, "He that is of the truth hears my voice." And Pilate says, "What is truth?" And if you read those John 18 and 19, he was not dismissive. In fact, he was very thoughtful, because he said, "This is the King of the Jews," over the cross. And people said, "Tear it down. He'd only said he was the King of the Jews." He says, "What I've written, I've written." And he said earlier, this man has done nothing wrong. He knew he was caught. He knew that effectively the man in the dock was the one who was in control of him, not the other way around, which verifies this statement. In him, Christ was there, fully in control of all the events at the cross. Even when he was on the cross, he was still sustaining everybody's breath by the word of his power. He was sustaining his persecutors by the word of his power. When we begin to get that in our minds, and we begin to realize that as the nails went into his hands and his feet, he was still sustaining the physics of those nails. He could have in a moment just come off the cross, but chose not to, because he loves us and he gave himself for us. Isn't that wonderful? That science tells you an awful lot when you really think it through. Kepler said, thinking God's thoughts after him, and I've just been quoting, that he upholds all things by the word of his power, including the free energy in the DNA bonds. May God bless you all.
Thank you, Andy. I think that was a wonderful ending of a fascinating talk, pointing towards the grace of God. He could have chosen to step down from the cross. And I really like that here you emphasized the parallel that on one hand you talk about thermodynamics and you cannot create free energy spontaneously, and then you talk about information, that information cannot be generated spontaneously. And then you beautifully connected the two through the Landau principle or the Landau limit, that there is an energy cost in terms of free energy for each bit of information. So it's really, and also these laws of thermodynamics that parallel the corresponding laws of information.
They seem to be. It was John Sanford, who was a lovely, humble man, if you know him. I've so much benefited from John. It was he who put me onto that idea.
And I think this was the final talk of this Creation Research Conference, and I think it beautifully connects to the other talks, because we have emphasized, we've heard several talks about creative kinds, or different aspects of creative kinds, so that God creating the first generation of each kind, and that is putting a lot of free energy or information into the first generation of each kind, and then
yes.
Speciation within each bush, and that is a kind of loss of information along the way, or so it's. I think
there's an energy penalty.
Yeah, so it really it gives a sort of thermodynamic or informational basis for creative time. So would you agree on that?
Yeah, I mean, I think there's a whole host of things here that we need to look at.
Yeah.
But I've only really just dabbled, put my foot in the water of biological systems. I'm learning from you guys.
Yeah, creation science is really cross-disciplinary. So
It is.
we all learn a lot now these 2 days, and so now we have time for questions. Yeah, we have. Nigel.
Nigel.
The thing about information is, typically we recognize it as information.
Yes.
So there's someone reading it.
Yeah.
How does that work in the cell? Is this all part of your machines, or what's reading?
Well,
Please don't misunderstand me. I totally agree, it's information.
yes.
But what's actually reading?
Well, we know the mechanics of how it's read. I mean, I'm not an expert, but I'm sure, Nigel, you know that apparently there is a whole system making sure that the appropriate amino acid corresponding to GCC is brought up at the right point, and then CAT spells for another. But something is still not telling me all the detail as to how it knows to go away and get the right amino acid. Maybe some of you, like Peter and you, know more than I do as to how it does that.
Yeah, well, you just...
So what is reading? How do you translate the word reading into what's going on in the cell?
Yeah. I assume that's why you struggle with, I wouldn't say struggle, but you have the three other aspects of Git's information team.
Yeah. Well, it's not that I struggle with them, it's just that it can confuse. I want to go 2 stages first. He talks about semantics and there's pragmatics, yeah. So there's yet more. But as long as we agree that there is at least 2, we see that there is a whole system here.
Yeah, you do push the problem one step back. The code, not the program, but the code itself has 20 amino acid tRNA synthetases. But then once again, what's actually doing that reading? And at the end of the day, we're pushing it back to our Lord, yeah, of course.
Well, we are, but it's very helpful to investigate this. And maybe you and Peter and others can tell me that there is how this reading, what's prompting the reading? What brings up the appropriate amino acid for CAT or for GCC?
Well, that's this amino acid tRNA synthetase. There's 20 of them.
Right, but somehow the machine, sorry?
Yeah, they connect the appropriate amino acid to the appropriate tRNAs.
Yes.
Yeah.
But that's only describing what happens. It's not actually giving you, I'm putting your question again back to you. It's not telling them why it does it.
The cell is a finite state machine, in fact.
That's interesting. Peter says it's a finite state machine.
Yeah, this is, in fact, I discussed this topic once with
I discussed this topic a while ago with a guy who was an engineer, and I explained to him what a cell is and how it works. And he said, "Oh, that sounds like a finite state machine." So then I looked up what it is. It is in engineering. It's a principle that is very similar to how cells work, with input and an almost automatic response. So it's running on itself, in fact.
So it's already set up to do that,
Yes.
and it always has been for the word go.
It gets the inputs from the outside and it works.
Yeah, no, okay.
Yeah, please.
Pika.
Thank you very much, Andy. That was fascinating. The folding of proteins, it's actually a chicken 2 eggs problem.
Chicken and 2 eggs.
Because you need chaperones to fold the amino acid chain.
Yeah.
That's a protein, chicken and 2 eggs. But this was funny, this 2 pounds of meat, Richard Dawkins' answer, because how does the 2 pounds of meat know that this 2 pounds of meat is Richard Dawkins? I mean, the self.
Exactly.
The question of self. We all know we're a person for self. That has no answer.
No.
I would like to ask you, is think about ancient DNA. There's a lot of discussion how long does DNA stay in the ambient in the world. So does this have a connection with the energy in the bonds of?
Yeah.
We could calculate the maximum existence of DNA because they say that the DNA millions of years old has been found. Do you have a comment on that?
Yes, I do. In fact, this is relevant to another issue on the age of dinosaur bones found with soft tissue in them. And it's not the only thing with living material which is found with DNA in. Leaves have been found still with DNA in the fossil, right? And so people have measured the half-life of basically DNA bonds. And yeah, it does take a while to deteriorate, but it's certainly, you're not going to have much left after a few thousand years. I can't remember what the figures are for the half-life, but it's certainly measured in centuries. It's not measured in millions of years. So it immediately destroys any notion of millions of years for any fossils which have got soft tissue in them and by implication DNA still there. And that applies amazingly to dinosaur soft tissue, which is supposed to be 65 million years old. It can't be. So there is a relevance to that.
Oh, more questions? Göran?
Horan?
I guess that what you have said about the free energy and so on, that doesn't, I mean, if you have a totally random DNA sequence, I guess there's no difference. It doesn't discriminate between a sequence which really carries information or it's just a random sequence. I guess it's not.
Exactly. It costs an energy penalty to store rubbish as well as to store information. That's your point. Yes, it does. So you cannot, using this, distinguish between what is true information and what is rubbish.
No.
You've got to have something reading it, struggling to read it and say this is not nonsense before you can actually decide. Yeah,
but
you're right.
Could you explain why there is an energy, a need for energy in just storing that unit of information?
Well,
is it just you have to put something in place, or it needs energy to do that?
well, if it didn't, if it was exothermic bonds, right, then all these biochemical bits would just snap together automatically, but they don't snap together automatically. You've got to have it such that you put energy in, otherwise you're going to get everything sticking to each other.
Okay, so it's a chemical matter.
It's a chemical matter. In fact, you need it, because otherwise there would be no rationale for saying this one goes with this one, and I've got to put energy in to make it work.
Okay, so it has to do with the DNA molecule or RNA molecule, or what is? I mean, a certain amount of energy. It must have to do with some chemical reaction.
Yes, it's a chemical reaction. It's literally a chemical reaction.
Yeah, and it depends on whether it's the energy in the peptide bond or is the energy in the phosphate bond.
We're not dealing with the phosphate bond on the chart that I gave you. We're dealing with the nucleotide bonds. So it's what's the right term for that?
Yeah.
Sorry?
Hydrogen.
It's just the hydrogen bond. Yeah, it's the OH. Sorry?
Diester bond.
Right. Okay. All the correct terms you've got and I haven't. So I'm learning from you, Nigel.
Thank you.
Yeah. So it's the nucleotides. Okay. Thank you for that.
So I was thinking if we compare the total energy content of a life form like Adam and Eve, we compare the total energy in that system compared to us today, can we say that the energy content of life has steadily declined over each generation?
That's an interesting question. The total internal or the total free energy take of all the millions of bonds in a human being is what's involved there. That would be very difficult to estimate. I think I wouldn't be prepared to make a comment on that, because clearly you're dealing with an open system which was sustained originally presumably by the tree of life, and that would be an ongoing raised free energy of the whole system, which is us. Now we don't have access to that. I guess something has definitely changed in terms of the amount of energy and the wastage that we have as well. I think it would be very difficult to do a calculation. I just have to say at the moment, pass on that. But it's an interesting point.
I was thinking in case like chromosome counts has declined, maybe the information content has maybe lost information compared to Adam and Eve.
I think information will have certainly been lost. I think you're right on that one. But whether the amount of energy connected with the storage of that information, I'm not sure. In fact, if anything, it might even have gone up, because we're probably storing a lot of mutations, storing a lot of stuff which has got twisted, and something's changed, hasn't it? Our system now decays and has to be kept going. There's a principle of death in us, which is probably very costly energy-wise, which wasn't there before.
I have a slightly connecting question, and it's perhaps not completely formed, but I'm thinking a lot about this, or how would you relate this to the amount of redundant information? Because if we look at, for example, you can transmit information, and we know it, especially these days with the large language models in AI, when they are trained on information, they don't store explicitly all the information sent, but they are formed and they are updating only when there is new information.
Yeah, that's true.
They are good at reducing the duplication of information. And I'm interested in if you have any comment on how this relates to the thermodynamics. Like, is the body good at trying to reduce the redundancy of the information? Or
we are not automatic machines, are we? We are probably storing a lot of information that we don't need. You're saying that, look, with what we heard on the talk before, we obviously have a whole set of DNA which people originally thought was junk, and you could have said it was just mere duplication. But actually it all needs to be stored, and the epigenetic system has to be able to access that. So
I could perhaps clarify, I remember now more clearly what I was thinking of also, like a way to quantify information. Like, you can quantify the information that is sent in channel information, but when you have duplication and when there's nothing new coming in, that is actually kind of, the true amount of information is actually lower if it's nothing new.
Repetition.
That is as long as you've already stored it, but you don't know whether you have to store it. That's the problem.
Yeah.
Because you might have thought, I was using really the idea of epigenetics, what we just heard, right, and the idea of junk DNA as an illustration. How do you know whether that's important to store or not? You think that it's just the same. Then it only materializes later. You need that bit because there's a system which is much greater, which is using that. So I rather think that we cannot just use the idea of, it looks the same, therefore we don't need it. I think we've got a much more complicated system going on, from what I gather, than might appear to be the case. So we do have to store everything. Sorry if I haven't answered your question too well there, Philip.
So, thank you.
Thank you. I've been teaching medical students for 20 years, and I always teach them this trick how to remember things. And the trick is as follows. You have to love what your, this is fantastic, you have to love it to take it in, to get the dopamine and endorphins turning, then you store it. Otherwise you lose it. Because this is awful, I don't want to hear this. You remember nothing.
That's a good point.
So that is the hard disk in your brain will never get full. The problem is to take something out of there. But it has recently been calculated the energy cost of thinking. As we listen to Professor Andy, our brain is working at full speed. If we would build a machine, a super computer which resembles our brain, it would need the electricity of several nuclear power plants to listen to you. But this we can listen with the breakfast we just ate. So it's an ingenious way of using electricity and biochemistry. That's very interesting because the firms working on nuclear energy power plants, they calculated how much would it cost if the same data processing was made with their machines that our brain does. It would cost many power plants.
Different order of magnitude, isn't it? Yeah. Well, thank you very much. Thank you, Pekka.
So we have time for one last question. Yeah. Peter?
Peter.
Okay, thank you so much, Jamie, for this excellent talk. I would like to know how in this triplets experiment on measurements of energy that you showed, how was this related to this Landauer? First of all, you said it was really close to...
It was close. It was about 10 times or less. Some of them were less than 10 times.
Okay, because then I have a question about how bits of information are...
Exactly. That's the question I still need to think about carefully.
Okay.
Some of them were close to being 6 times, but I rather think you can't go below 6 because I think the minimum amount of information in a triplet of codons is, if you work it out, it's 3 times 2 times 1, so it's 6. So it's going to be of that order, and that's what Salvador pointed out to me. And I'm thinking of writing a secular paper on this, right? I haven't yet done it, which will talk about what is a bit of information, and then apply, perhaps write it with Salvador, at least certainly acknowledge his input, because he's a very thoughtful gentleman. And anyway, whoever writes it, but it needs to get it out into the secular literature. And I haven't yet done that. But sorry, carry on, Peter.
This was also my point, because in every position in the DNA or in the nucleus, there's 2 bits of information. So it would add up to 6. This was my point.
Yeah.
I think then you're exactly on the line.
You're extremely close. You won't be exactly at it. There'll still be a little bit of entropy, bit of loss. But it's so minute. I mean, information scientists would be scratching their heads to make a system like it. Because the amount of energy loss is very, very small indeed.
Very interesting. Thank you very much.
But I'd be interested actually in going further and saying, well, what is the energy needed to make an amino acid and to bring an amino acid along to actually read this particular system? Because then that's carrying information. And then you bolt it onto another amino acid. So all the time you've got energy costs, but they must be very, very small indeed.
For making an amino acid, it will be much more, I guess.
Yeah, I presume it will be, but I need to work on that.
So, and if you have more questions, you can ask them to Andy during the lunch later on. Again, this is very stimulating with all these questions. And let's thank Andy again for his excellent talk.
Thank you.